In this video, we'll explore prime numbers. A prime number is a whole number that is divisible by 1 and itself. For example, 29 is only divisible by 1 and 29, so it is considered prime. With the fundamental theorem of arithmetic, what that states is that every whole number greater than 1 can be factored as a product of prime numbers. For example, 30 is the product of 2 times 3 times 5. Now, something that was found by Eratosthenes is called the sieve of Eratosthenes. And this method is a way that we can find and list all the prime numbers. First, we start the number 2, and then we choose any stopping point of our choice. We circle 2, and then cross out every second number, i.e. the multiples of 2. And we continue to do that by going to the next uncrossed out number, circle it, and then use it to count to the nth ones to cross out. And we do this until all we're left with are primes between 2 and our stopping point. So say we want to do up to 40. First thing we do is we list all of the numbers starting at 2. So I circle 2 and I cross out every second value. You see, so there goes all my evens. Well, the next number left is 3. So I circle 3 and then we'll cross out all the third values. So 6, 9, all my multiples of 3. Now I'm going to do the same thing for 5. I circle 5 and cross out the fifth item each time. Then I go up to 7 and cross out the seventh. So take out 14, 21, and 28. With 11, I'm only going to mark out 22 and 33. 13 takes out 26 and 39. 17 crosses out 34, and 19 crosses out 38. Now what I recognize is that at 23, if I go to the 23rd item, I'm beyond 40. So every number that is not crossed out at this point is prime. And there's my list of primes between 2 and 40. Now if I need to determine whether or not a number is prime, I can use a trial by division. Here I'm going to be given a number, and I'm going to divide that number by prime numbers starting at 2. If it's divisible at some point, then the number is not prime. If it is not divisible, then I go to the next prime number. And I'm going to continue testing until my quotient is smaller than my divisor, because at that point I know that there's nothing I can divide by. So say 283. 283 divided by 2, not divisible. I try 3, not divisible. I try 5, that's not divisible. Try 7, it's not divisible. Go to 11, go to 13, and then I go to 17. Well, what I notice at 17, it's still not divisible, but now my quotient is smaller than my divisor. That means there's no more values I need to try. So 283 is a prime number. How about 133? If I divide by 2, it's not divisible. Divide by 3, not divisible. Divide by 5, not divisible. But when I divide by 7, it's equal to 19. Therefore, 133 is not prime. Now, one other thing we use prime numbers for is to create factor trees. And it's a visual way that we can create the factors of a number. One thing we want to make sure is after we create our trees that we list our factors in order from least to greatest. So say we wanted to create a factor tree for 120. So I start with 120. Now I can divide it by any factors I know. I know that 12 times 10 will make 120. Now I'm going to split each of them. I know that 12 is divisible by 4 times 3. And I know 10 is divisible 5 times 2. Now I know 4 can be divided into 2 times 2. 3 is prime, 5 is prime, 2 is prime. So I've now factored my 120. And if I circle all my prime factors, I know that those are my values that are going to be creating the product of 120. So 2 times 2 times 3 times 5 times 2. But I do want to go back now and reorder them so that I know that 120 is equal to 2 times 2 times 2 times 3 times 5.